the curl of a vector field. Consider the vector field F equals Pi plus Qj plus Rk, and suppose that the partial derivatives of P, Q, and R all exist. Then the curl of F is given by the determinant of the matrix here, which equals a sort of cross product on the del operator with our vector field. Well, the del operator is like a gradient operator. So let's find the cross product of this. We're going to do I times, and of course, normally we would say this thing times this thing, but it's really the partial derivative with respect to y operating on r, and then minus this, not times that, but the partial of q with respect to z, and then minus j, and we get the partial of r with respect to x minus the partial of p with respect to z, and then finally plus k, and we have the partial of q with respect to x minus the partial of p with respect to y, which should look familiar because we did this when we were doing Green's theorem. Now, one quick note, this is perfectly fine, but most textbooks will write this middle part as plus j and then simply flip the signs on the inner part, like that. Everything else the same. So, what's going on? Well, we did talk about this before when we were doing Green's theorem, but I do want to remind you, and I'm going to go down to this third one here, where we said this part here, notice that we have q, which is related to y with respect to x, and then p, which is related to x, and then with respect to y. This is talking about a rotation in the xy plane. Where we have some sort of rotation like going around the z-axis. But then this manifests itself in the z direction. And we talked about the right-hand rule when we did that. So similarly, if we were to do this first one here, where we have r, which is related to z, but partial with respect to y, and then q, which is related to y, but it's the partial with respect to z. So imagine that you're in the yz plane, and if there's some sort of rotation, it can manifest itself in the x direction. And of course, similarly for this middle one as well. So recall that curl, like if I was to draw the curl just in the xy plane, I like to think about as a rotation. Now, where do you think we got the name curl from? Something like that. So let's do an example. Let's find the curl of f. I wrote the formula down here for us so we don't have to go back and look. But f of xyz equals xzi plus xyzj minus y squared k. So the curl of f is going to be the partial of r, so r is back here, with respect to y, minus 2y, minus the partial of q, the middle one, with respect to z, so minus xy, I, and then plus, do the j component, partial of p with respect to z, which is x, minus partial of r with respect to x, which is going to be 0, j. And then finally plus the partial of q with respect to x, so the middle part with respect to x is going to give us yz, and then minus the partial of p with respect to y, which is going to be 0 and k. And this is the curl of f. Quick theorem. If a function f of xy has continuous second-order partial derivatives, then the curl of the gradient of f is the 0 vector. And we can do this proof pretty quickly. So the curl of the gradient of f is this. It's going to be the del operator acting on the gradient of f, or gradient of f is down here. So we're going to get I, and then the partial squared of f, y, then z, minus partial squared of f, z, then y. And we could continue. We kind of don't need to because we see what's going on, but let's finish it off anyways. The j part will be the partial squared of f, x, then z, minus partial squared of f, z, then x, and then plus k. And we have the partial squared of f, x, then y, minus y, then x. And notice, because we have continuous second order partials, that the mixed partials are always equal to each other. So we get 0, 0, and 0, which gives us the 0 vector. So the result of that is, if our vector field is conservative, then the curl of f always equals 0. That is, it always equals the 0 vector. So let's do another example here. Given this vector field, f of x, y, z equals y squared z cubed I, plus 2xy z cubed j, plus 3xy squared z squared k. Let's start by showing that f is conservative. So we're going to take the curl of f to do that. And we have the formula again right above us so we can see it. So the partial of r with respect to y, remember this back part is going to be r, is going to give us 6xyz squared minus the partial of q, recall this is q, with respect to z is going to give us 6xyz squared. And then I'll do it down here, plus partial p, and of course this is p. With respect to z, it's going to be 3y squared z squared minus partial of r with respect to x will be 3y squared z squared. And then j. And then finally the k part plus partial of q with respect to x, so 2yz cubed, minus the partial of p with respect to y, 2yz cubed. And notice that we get 0i plus 0j plus 0k, which shows that f is conservative. And since f is conservative, f must be the gradient of some function f of x, y, z. So let's write this again just so we can use it and see it. We have y squared z cubed I plus 2xy z cubed j plus 3x y squared z squared k. And we've done stuff like this before, where we found f of x, y, z is going to be the integral of the partial of f with respect to x dx. So this first part is the partial of f with respect to x. So if I integrate that one, we're going to get x y squared z cubed plus, right, so integrating with respect to x, the y and z are held constant, and then we assume that there's some function that's of y and z only. because when we take the derivative of that, the partial with respect to x, that would go to 0. Now, taking the partial of what we just found, but with respect to y, we get 2xy z cubed plus the partial of g with respect to y on yz. But I know from right here up that equals 2xyz cubed. What does that tell us? Well, it tells us that the partial of y, that is partial g with respect to y of yz, equals 0. Meaning that g of yz must be a function of z only. Because when we take the partial with respect to y, there's nothing left. All right, so let's do one more. Actually, let's rewrite this up here. We have f of xyz is now xy squared z cubed plus h of z, right? Because g of yz is h of z only. And if we take the partial of this with respect to z, we get 3xy squared z squared plus h prime of z. But from back here, that being f of the partial of f with respect to z, which says it's equal to 3xy squared z squared plus 0, if you would, that implies that h prime of z equals 0, which means h of z is simply a constant. And then we get our original function, f of xyz equals xy squared z cubed plus c.